Here we go. Good morning, everybody. Good morning, YouTube. And we're back in business. I just want to say that basically for the rest of the semester, and until I think I might indulge myself for maybe the last lecture or two and just talk about something kind of related to Galois theory, but that's actually more closely related to my own research. Just because, just to maybe give you guys a little breather is like to the onslaught of new material. Anyway, or just maybe, okay, it's mostly to indulge myself, but still. So for today, the reading was 16.7 and 16.8. So we're going to go over, we're going to finish up a little bit from the main theorem of Galois theory and move on to cubics. And then we're going to, and then on Wednesday, we'll start quartics. Oh no, wait, today is Wednesday. Every day is the same now, right? So for Monday, yes, for Monday, we're going to do quartics 16.9. There's a problem set 10, which is due on Monday, April 27th, and then the week after that, we'll try to do one more take-home midterm, just to sort of keep everybody focused. And we will have a problem session on Friday from 10:30 to noon. Yeah. Okay. And so, any questions before we get started? Oh yeah, that's right. And I was going to turn on my in some sort of futile attempt to make this slightly more visually interesting. Okay. Oops. Okay. Let me hide non-video participants so you don't have to keep a record of your attendance on YouTube. Sorry about that, everybody. Yeah. So I guess we'll see. We'll see if this makes it having my little head in the corner makes it slightly more visually interesting. Hello from my little head. Let's see. Right. See if I've mastered this. So everybody, am I pointing towards the slide now? I should be pointing towards the slide. I don't know. Was I? Can everybody say in the chat? Was I pointing towards the slide? Yes, I was pointing towards it. Kind of. So like the slide is over on this side, and then down over here, and then down here. Is that right? Can you say it in the chat? I'll see in the video. It's fine. Yes. So something about putting my picture in the corner turns me like even more immature than I usually am. So, well, that's the price to be paid, I guess. All right. Any questions before we get started? Oh yeah, Mungru asked, when does exam 3 start? I don't know. I'll probably hand it out. I'll probably hand it out about a week from today. That's right. I should probably write that, huh? And then, but you know, all deadlines are incredibly elastic. I'm not. I don't think I've collected all the exam 2s yet. So I certainly haven't graded them. So you know, it is what it is, right? Okay. So any other questions? Mungru, that was a good question. Robert, that was a very catchy tune. Okay, let's get going. So we're yes, right. So as always, we're going to start off with our recap of Galois theory. Oh no, we are not going to start with the oh, I erased my recap. Oh well. Well, let me see. All right, then this is going to be totally dangerous. I'm going to try to do my recap of Galois theory, but I'm just going to try to do it off the top of my head. Famous last words, so you can see me crash and burn on YouTube. Oops, I already messed that up. Okay, there we go. So now we want to do a recap of Galois theory, which a slide I totally forgot to put in here. So the situation is that we have F as a field of characteristic 0, and K is a splitting field of some f of x in f bracket x. Let's see, and so in particular it's a finite extension of f, and we let G be the Galois group of K over f, and then let's see. So what's important here? So I guess So in practice, what do we want to do? So the point is that the group theoretic, the overall point is the group theoretic structure of G has close analogs in the field theoretic structure of K as an extension of F. Oh yeah. Oh shoot! I should probably remind you what G of K. There's the group of F automorphisms of K. In other words, the automorphisms of K that fix every element of F. All right. So that's so the group theoretic structure of G has close analogs in the field theoretic structure of K as an extension of F. Yeah, one example, the sort of first and most prominent example is that the order of the group G is equal to. Why did that not work? There we go. I don't know why it stop typing there for a minute. It's equal to the degree of K as an extension of F. So one of the I guess maybe not. I guess actually here is a good place to stop and sort of change colors. So that's kind of where we are so far. And now let me try to use a genuine purple as opposed to the thing that I've been using so far. So now the current problem that we face or that we will face in a few minutes after we clean up a few things having to do with in the part of the main theorem of Galois theory. The current problem we face is given f of x in f bracket x, I guess, and sorry, given irreducible. Well, possibly irreducible, though not always. In fact, we saw last time we looked at a non-irreducible example. And K, the splitting field of F of little f of x. We want to the sort of problem that we set ourselves for the rest of the course, which has a sort of eventual theoretical sort of overall global consequence. But right now we're just thinking about it like so here's a problem to compute. How do we compute the Galois group of K over F? And this you know if you go get a PhD, as I know some of you are planning to do, this is like a classic kind of problem to assign somebody. You write down a little f and usually a rational little f. You say, tell me what the Galois group is. Compute the Galois group of the splitting field of that little f. And right, this is a classic PhD qualifying exam question. Given a rational polynomial, actually usually usually irreducible, f some particular irreducible polynomial with integer coefficients, compute the Galois group of its splitting field. So well, I guess it's not exactly applied math, but for those of you who might be planning to go on and get PhDs, it's applied to the problem of finishing your PhD. That's a good That's a good application. Anyway, so what are some things we can use to compute G? One of the most prominent things is that G acts on the roots, well, not acts on, it permutes the roots of f of x, even when All right. Let me. Oops. I see a question. All right. So yeah. Robert points out that it's interesting to think about error correction codes and apply to them. Yeah. Well, you know, actually, I'd say I don't actually know any applications of Galois theory to error correction codes. Robert, do you want to say what you mean by that? Oh, you just think, okay, I see. Yes. So I mean, yeah, I bet there is. I bet if you Google something, you know, oh, you know, I take it back. Uh, so yeah. So Robert says, you know what? I say I don't know. I don't know anything about the application of Galois theory of the error correcting codes, but actually that's completely wrong because at 10:30 I'm going to give a lecture about the application of Galois theory to error correcting codes. But it's actually Galois theory. Yeah, you can actually use Galois theory. So let me make that as a kind of an aside down here. Aside. In my undergrad class, applied algebra, I'll be talking about I'll mention one. I won't use the words Galois theory, but I will actually use the word field automorphisms for what it's worth. One application of Galois theory here today. Galois theory to error correcting codes, to constructions but this is that, but that's actually characteristic P or characteristic 2 is the money maker, right? Because I mean the theory. I mean, and to be fair, the theory is like way simpler. It's I mean, there's actually a really neat theorem that it's always, if I remember correctly, that the group is always cyclic, but you know, still, but the application is really neat. You actually apply Galois theory to compute the minimal polynomial of a field of like an element of F16 over F2, and so which turns out to be very useful to constructing good error correcting codes. Anyway, I don't know. If you're bored, stick around till I'll give you the link at 10:30, and then you can just watch the my undergrad lecture on YouTube. Anyway, sorry, that was a total digression there. All right, sorry. So things, but okay, going back to sort of our immediate problem, things we can use to compute G. Right, actually, well, this should actually should be blue, but we'll talk about it again. So G permutes the roots of f, our split polynomial f of x, even if f of x is reducible, and if f of x, but perhaps more importantly, if f of x is irreducible, then G acts transitively on the roots of f of x. So this, oops, I made that too big. Oh, well, it's fine. This root permutation representation of G is faithful. And remember, G, that means G is isomorphic to its image, to the resulting image in its to its resulting image in Sn. Imagine image in Sn. So G is isomorphic to a subgroup, a possibly transitive subgroup if little f is irreducible. Okay, so sorry, I got kind of derailed. I just totally made that up, and then totally derailed myself there. So let's pull back, and I'll just repeat all that again. Okay, whole page. Oops, that's a little tough to read. Okay, so again, to recap Galois theory, so we have our usual situation where f is characteristic 0, and k is a splitting field of little f and big F, and capital G is a group of f automorphisms of k. And the whole point of this is the group theoretic structure of G has close analogs in field theoretic structure, and of the field theoretic structure of k as an extension of F. I guess let's say C, the main theorem of Galois theory, which we're about to restate. So for example, just as one very sort of first example, the order of G is equal to the degree of k as an extension of F. The current problem that we're facing right now in section starting in section 16.7 and pretty much going to the end of the chapter, given an irreducible little f of x and little f and big F, how do we compute capital G? And two facts that we can use to, well, basically our sort of first fact we can use to compute capital G is that capital G permutes. Besides the fact that the order of G is equal to the degree of k as an extension of F, is that G permutes the roots of F, even if you can factor F, and if F is irreducible, sort of the most interesting case, then G acts transitively on those roots, and we can always, which means, as we'll see later today, we can always think of G as a subgroup of Sn, where n equals the degree of F. So G is isomorphic to a transitive subgroup of Sn if F is irreducible. And so one of the first steps that you take in when you compute a Galois group is that, well, if you look at the degree of n, and the sort of degree n of F, and you say, well, what are the transitive subgroups of Sn? You sort of write them all down, and that immediately limits your possibilities by quite a lot. Whew. Okay, so any questions so far? And I think, I guess I should say that I've sort of abandoned somewhat at this juncture the sort of motivating problem that we were talking about earlier, which is that we want to show that the fifth degree, the quintic, is not solvable, that is not solvable by radicals, but that will basically boil down to computing capital G. So so there we go. So any questions so far? Boy, it would have saved me a lot of time just to have remembered to put down that slide, huh? So are we good with our recap so far? Say yes. Okay, so let's continue. All right, here's the main theorem of Galois theory. Just a little bit more review in some ways. So again, let K be a Galois extension of F, which is another way of saying that K is a splitting field of some polynomial in big F, and let G be the corresponding Galois group. Then we have a bijective correspondence between subgroups of G and intermediate fields. And so let me see if I can draw that correspondence a little more telegraphically than last time. I think oops. All right, so yeah, let's do the short version here. So the idea is that if you look at the lattice of the subfields of K containing F, so this is all the intermediate fields L between K and F, including K and F itself. Then let's see. So here's the big field and the small field. I find it kind of helps to think about this on this kind of childish level. Here's the small group and the big group. There we go. And then and the correspondence is that so the first thing to remember is that this is inclusion reversing. So I think so this means that pointing down means you point down towards the smaller things because the smaller things are contained in the bigger things, and the arrows point towards the smaller things. Right, there we go. And the picture to remember is that let me switch colors here. Is that the bijection is going one way sends H to its fixed field, and the correspondence going the other way sends L to now. And this is the part that always confuses me, but I guess it kind of makes sense given that this L corresponds to this subgroup H over which sort of relates to. Well, let me blow this up here so you can see more of what's going on here. There we go. So the correspondence going this way, I think I did that right, sends the group H to its fixed field, and the correspondence going the other way, remember to mirror this, it sends L to the Galois groups, of not L over F, but K over L. And we're just about to get to right. G of K over L sort of operates over here. So, and that's the thing that's I always find very confusing, but I hope this picture helps a little bit. So that would, I feel like I'm doing like an infinite series of recaps. I'm hoping that if I make each one half the length of the previous one, then the series will sum and I'll be able to finish this lecture in a finite amount of time. Ha ha ha! Analysis joke. Okay, everybody good so far with that picture? So that's the main theorem of Galois theory, which that was last time. I know you're all saying like, "Oh my God, we're 1/3 of the way through. Will he just go on and say something new for God's sake?" Okay. All right. Let me actually go do that. Normal subgroups and extensions. Okay. So the Galois theory, like I was just saying, one of the I mean, at least for me, confusing things of Galois theory is, but that's the way nature is, and you can't argue with nature, or at least it's a very one-sided argument if you do. That the Galois theory of the intermediate field over the base field of L over F as opposed to K over L works much less well than the Galois theory of K over L, right? We saw, or maybe not less well, at least it's more complicated. Yeah, that's a long enough word that I want to say that, type it. At least it's more complicated. / confusing. It works less well is the right term, but at the very least, it's the Galois theory of when you look at intermediate fields over the base field, it's more complicated or confusing than the Galois theory of the big field over the intermediate field. So, what do I mean by that? So, but on the other hand, you can state it very precisely. So, suppose K is a Galois extension of F, and let capital G be the Galois group of K over F, it's the full Galois group. Let H be some subgroup of G, and let L be the fixed field of K. So that's sort of in other words, let H and L correspond to each other over here. Then L is a Galois extension of the base field. So when does this extension work sort of nicely? When is that a Galois extension? Exactly when H is a normal subgroup of G, in which case the Galois group of L over F. Oh, there's a lot of slashes here, so let me emphasize what this slash means. So this is the quotient group. So when H is a normal subgroup of G, or equivalently, when L is a Galois extension of F, then the Galois group of L over F is equal to the quotient group G mod H. Huh. Cool. All right. So let's prove that. Yeah. So do I have enough room in this picture to? It may have just enough room. Yeah. Let's go back. Let me go back and sort of complete this picture, and I'll use one more color. So this is Galois exactly when H is a normal subgroup of G, and in which case the group G of L over F is equal to G mod H if G is normal. If H is normal in G. There we go. That's a gnarly looking equals there. Anyway, yeah. So that actually, I guess in some ways that this text in blue completes the main theorem of Galois theory. Exactly. So when can you sort of pass the time when you can sort of pass the Galois theory of K onto the intermediate field L is exactly when H is a normal subgroup of G. Okay, so let's go prove that now. So as always, well, not as always, but as we often do, our first step is because we're working in characteristic 0, let L be let epsilon 1 be a primitive element of L over F, and let G be the irreducible polynomial for epsilon 1. Okay, the splitting theorem, right? So I think this is I think this is the first time I've taught Galois theory in like 10 years, and this is certainly the first time I've taught Galois theory in a graduate class. So I've never really gotten quite so deep into it. And so, I think when I introduced the splitting theorem, I said, well, I'm not exactly sure what this is for. Here is one place where the splitting theorem is actually very important. So by the splitting theorem, there we go. So remember, the splitting theorem says that what does the splitting theorem say? I should let me remind you, maybe remind myself as well. The splitting theorem says that it's a slightly subtle thing. So the splitting theorem says that any irreducible with a root in a splitting field K splits completely, not just the one we started off with. Right. So remember, the assumption up here that K is a Galois extension of F means that there at somewhere in there is some polynomial little f such that K is a splitting field of little f. Okay, so there is some original splitting polynomial, but the splitting theorem actually says that every other irreducible polynomial in big F, with coefficients in big F also splits in K as long as it has one root, and yes, it does, because there's just one root. So we know that all the roots of G are contained not just the one root, but all the roots of G are contained in K. Yeah, so all the roots. So we also know, because, and this is sort of a generalization of something we were saying before. Well, actually, we know that symmetries of G preserve F, and so they must preserve roots of little g. So capital G acts on epsilon 1 through epsilon sub r. G is transitive because G is irreducible. That's the symmetrization theorem that we saw a couple sections back. So G, in fact, acts transitively on, I should say transitive on what? Transitively on these guys, on epsilon 1 through epsilon sub r, where r is the degree of G. Let's see, what else do we know? We know that L, we know from the characterization of Galois extensions that L is a Galois extension. Exactly, I guess I should say L over F is a Galois extension if and only if L is a splitting field of some polynomial, if and only if all of the epsilon sub i's are in L, right? So because, again, by using the splitting theorem, the epsilon sub i's are in L exactly when well, I guess let me so here's a slightly less immediate statement. Which is that a root epsilon sub I is in L exactly when L is equal to F of epsilon sub I. I think this direction, I think, is not hard. So let me talk about the other direction. Actually, I want to say proof of this direction. If epsilon sub I is in L, that implies certainly that F of epsilon sub I is contained in L, right? And because we know that F is contained in L, and then we apply the fact that the degree of F of epsilon, the degree of F of epsilon sub I as then we use the degree of the extension. Oops. Actually, then we're going to use the fact that the degree of F of epsilon sub I over F is equal to R, which is equal to the degree of F of epsilon sub 1 over F. And so if you have a subfield of an extension that has the same dimension, it must actually be the whole thing. Anyway, so that wasn't too quick. I worry that was a little too quick there. Should I explain this point here again? Should I talk about this again? Yes or go on in the chat. Yes, I should talk about that again. Okay, so all right, so let me try that again. I did that too quickly. My bad. All right, so pen page. Okay. All right. So suppose epsilon sub I is in L. So this is a useful argument to know about. Then it must follow that F adjoin epsilon sub I is contained in L. Okay, great, because F is contained in L. But since the degree Oh, and remember, L is by construction f of epsilon sub 1. But since the degree of of the element epsilon sub I is equal to R, because epsilon sub I has the same irreducible polynomial as epsilon sub 1, we know that that the degree of f of epsilon sub I over f is also equal to R, which we know by construction is equal to the degree of f of epsilon sub 1 over f. And this is a little argument that kind of shows up offhand a couple times in Artin, so it's definitely worth discussing. So f of e sub epsilon sub I is an R-dimensional subspace of the R-dimensional space f of epsilon, well, f of epsilon sub 1, which is L. Oops. Sorry, I started confusing degree, and we're done. So does that make sense now? Does that argument expansion help there? Okay, yeah. So great. And returning to our laundry list. Oh yes, and the stabilizer. Oh, so finally, the stabilizer in G of epsilon 1. So, well, that's equal to the stabilizer. Oops. Stabilizer in G of the field L, because everything in G fixes all of F. Everything so if you have an element G that also fixes epsilon 1, well, then you have to fix all of L, and so that is going to be equal to H by the Galois correspondence. Okay, so all right, so we have that. We have those 5 facts, 4 of which, the 4th of which I think took a little more thought than the others, and I think the other ones are a little bit more familiar. Okay, so this is what we know of the situation so far. So so are we good with these 5 facts? Say yes, or ask a question. Can you guys hear like the traffic and construction noise from outside? It's like having class outdoors or something. Or something. Okay. All right. So we have those 5 facts. Whoa. All right. So let's continue the proof of normality. So now, so we know that G. From the first 2 facts up here, we know that G acts transitively on the epsilons, on the roots. And remember, I guess maybe I should copy this over. So this, remember that the epsilon sub I, epsilon 1 through epsilon R are the, so we have that L is F adjoint epsilon sub 1, epsilon sub 1, and that epsilon 1 through epsilon sub R are the roots of, all of the roots of the irreducible polynomial G of X of epsilon sub 1. Okay, so now, since G acts transitively on those roots, choose some sigma sub I, such that sigma sub I of epsilon 1 is epsilon sub I. Well, so I claim, what do I claim? I claim that the stabilizer in G of epsilon, so we know that the stabilizer in G of epsilon 1 is H, and now I claim that, that the stabilizer in G of epsilon sub I is, and actually let me sort of try to remember, I'm going to try to remember how what to do here in front of you. So this is, so I'm not going to fill it in quite yet. A conjugate of H. Sorry, so this is, it's either going to be sigma H, sigma inverse, or sigma inverse H, sigma. Let me see if I can remember which is which. Okay, so let's see. So it's going to, so suppose, so I'm going to fill this in a bit. Suppose, let's call this element little g is in the something or other conjugate of H. Then, all right. I don't think I've said this in this class. So it is. So here's a sort of here is a hidden truth about mathematics. Like, and when you do research, you really are drawn to this. In a math class, right? It goes, you start with the definition, and then you have a theorem, and then you have a proof. But in reality, what do you actually do when you do research? You find a proof, and then you figure. I mean, you're just sort of like messing around. You find a proof, and and those of you who have done research, and the couple of you done research with me, when you do research, you find the proof first, and then you think, okay, what is it that we just proved? And then you go back and you read the definitions to make it look better. That is, of course, the honest way of actually doing this sort of thing. All right, so we're actually going to do this here. We're going to figure out the proof and then go back and write down the theorem. Suppose G is in some conjugate of H. We know something like that to be true. Then it must be the case that that we want that epsilon sub I. When you apply G to epsilon sub I, this is going to be G applied to sigma I of epsilon sub I. Oops, I forgot to say. Then G is equal to something H something else for some little h, for some little h in big H. Right, and now here, okay, now I figured out what the theorem is, because in order for H, oops, except I made a typo. I wonder if the chat, typo E1, yes, the epsilon 1, that's right. So I made a very important typo here, my bad. So this should be, look at that. Just like I meant it before, so I was saying before, I was so rudely interrupted. Right, so epsilon sub I is equal to sigma of I applied to epsilon sub 1, there we go. And so here we're gonna still have, sigma sub I applied to epsilon sub 1. And now what we know is that we want whatever we want over here and over here to sort of cancel out this sigma sub I. So now I know to write in here. So now I know that we need to have a sigma sub I inverse, sigma sub I, sigma sub I inverse. And so G had to be equal to sigma sub I times sigma sub I H, sigma sub I inverse. And so the theorem is that we're going to show that the stabilizer of epsilon sub I is going to be sigma sub I, sigma sub H, sigma sub I inverse. So it's a left. So I guess I knew that, I mean, you wouldn't. This is not what you think at first, but eventually you might realize, oh, it's going to be a conjugate. And then I personally always think, oh, is it going to be a left conjugate or a right conjugate? And sort of, and that's actually the proof that tells you, oh yeah, in order to get this cancellation here. So the whole point of this kind of proof is to get this kind of cancellation here. Yay! That's like a little mini triumph in the proof. Let me make sure my phone is turned off. I know it just rang. Okay. So this exactly this little mini cancellation here in the proof is what tells us what the theorem is. Like I said, first proof, then theorem, and then later definitions. Okay. And because actually it's actually this result and all of its friends that inspire the definition of conjugation. The reason that we care about conjugation, I mean, okay, this is maybe a bit of an overstatement, but basically the reason that we care about conjugation, if you remember back in 221A, you talked about conjugation at some point, and the reason that we care about conjugation is because conjugation corresponds to stabilizers of different elements of an orbit. At least, that's like the way I like to think about it. All right. Did I mention that I'm now speaking in my native dialect now of my native tongue, and so now things are getting really deep. Anyway, okay. So once you do that, so then this is equal to well, let me finish up the proof, and so this is equal to sigma I times h of epsilon sub 1, which is sigma I of epsilon sub 1, and that this and this follows because big H is a stabilizer in G of epsilon sub 1. And so and now our final expression is that we have sigma I of epsilon sub 1, which is epsilon sub I. So the point is G is in the stabilizer of epsilon sub I in G, in big G. Okay, yeah, so this is, that's one direction, and, oops, I little using, and the other direction is similar. Actually, let me just type that out. It'll be a little smaller, oops. Other direction, similar. Yeah. So this direction. So what we have, what I typed out formally says that if you have something in this conjugate. So yeah. So let me go back and let me go back and really state the theorem. If we have some other, so the point is that the stabilizer of epsilon is going to be the stabilizer of epsilon psi is exactly sigma sub I, and so we want to show that stabilizer is equal to this conjugate of H, and on the one hand, suppose G is in that conjugate of H, and so this calculation here. Actually, let me pull back and show the whole page. So if G is in this conjugate, then this calculation here, which we knew is going to work out that way all along. Okay, yeah, we worked out the proof, and then that told us what the answer was. Anyway, but this calculation here shows us that that G and every element is conjugate stabilizes epsilon sub I, and a sort of analogous and a similar sort of, if you do the whole thing backwards, more or less. Well, you can either do the whole thing backwards, or you could just sort of do the same, apply the same argument for the sigma I inverse, more or less. Anyway, so this tells us that the conjugate is contained in the stabilizer, and an analogous argument shows that the stabilizer is contained in the conjugate, and so we're done. And so we're happy with our little mini proof in here. Even if that's a little bit messy, sorry. Oops. And now, oops, no, that's not what I wanted. I wanted a page width. There we go. And okay, so now that we're done with our little mini proof, we see that returning to our the big picture, we know that L is a splitting field if and only if all of the epsilon sub I are in L, which means that which is true if and only if all of the epsilon sub I are stabilized by H, which is true if and only if all possible sigma conjugates of H are equal to H, which is the same thing as saying that H is normal in G. Ooh, there we go. There are more chains to that if and only if than I thought. So let me clean up this typography over here. But you know, there we go. All right, actually, and then let me review that again from the other way around. So H is a normal subgroup of G, if and only if all of its conjugates are equal to itself. Which is true if and only if each of those epsilon sub i's are stabilized exactly by the subgroup H. There we go. Stabby. That just looks like the word stabby now. Stabilized by capital H. And that's true if and only if, as we saw up there, all the epsilon sub i's are contained in L, which is true if and only if L is a splitting field. There we go. So L is a splitting field if and only if H is normal in G. Yay! Oops. So questions about that? So is that good, or are we good? Are we good to move on to the last bit, or are there questions? Say yes or put a question in the chat. Right, let me pull back so everybody can see the whole page. Could just be that's a lot to take in, but this kind of, I mean, this is actually, I don't know if you can tell, this is like one of my favorite arguments. That it's a sort of general principle that it is a lot to take in. So always the case, it's always the case that other stabilizers in the same orbit correspond to conjugates. Huh. Yeah, I mean, you know, so that's like a deep thing. As the Buddhist said about the hot dog, make me one with everything, right? Or the vegan hot dog, I guess. Anyway, so yeah, so it's always the case that when you look at stabilizers of other elements of the same orbit, those correspond to conjugates of the stabilizer, the first thing. Yeah, and that's really all that's going on here. Did y'all see this argument in 221A at some point? Do you remember? Yes, no, shruggy. Anybody want to say in the chat if you remember this argument from 221A or 128A, or no, probably not 128A, but 221A? Anyone? Okay, so yeah, Trent's seen it before, but okay. And anyway, it's a great argument. This is like one of my favorite arguments, and that's probably enough of it for now. All right, oh, something, I'm missing something in the chat. Okay, yeah, so, right, oh, right, so now we're talking about, so now suppose L is Galois, which is the same, I think I should have said if and only if here. So suppose L is a Galois extension of F, and which is the same thing as saying that A is H is a normal subgroup of G. And so now, what is the kernel of the action on of G on that orbit? Well, that's equal to so the elements of G that stabilize that stabilize all of the epsilon 1s through epsilon r's. Right, so if you stabilize all of them, that means you have to be in the intersection of all the stabilizers, which means that you, right, it's the intersection of all the stabilizers. Which is the intersection of all the conjugates of H. Well, but H, and actually one as I'm writing out this argument, I realize that one interesting thing that's going on here is that this is all true, even if H is not normal in G. So even if H is not normal in G, everything up to here is actually everything also works. But now that once we know that H is normal in G, which we were just assuming, the intersection of all the conjugates of H is just H. So yeah, so the kernel of the action on these elements is just H, and so the action of G on those elements gives an injection of G mod H into the Galois group of L over F. And why is it injection? It's the first isomorphism theorem. Look, we actually used the first isomorphism theorem. Remember that thing in combat, so to speak. So you don't get to do that very often, actually, and so it's always notable that when you actually get to do that. So you don't use it that often, but when it works, it's really helpful. Anyway, so the action of G on those roots of little g, epsilon 1 through epsilon r, gives an injection of the quotient group G mod H into the Galois group of L over F. And so let's compare the orders. Well, let's see, I'll do the easier one first. By construction, right? By construction, epsilon 1 through epsilon r, those are the roots of the irreducible polynomial for epsilon 1, and L is equal to f of epsilon 1. Oh yeah, and we know that f is Galois over f, and so this is just going to be equal to the degree. So because remember, L is equal to f adjoint epsilon 1. So this is equal to the degree of epsilon 1, which is equal to r. Okay. And converse, but on the other hand, the order of the quotient group G mod H is equal to the order. Well, it's equal to the order of G over the order of H, right? By like cosets. It's by like cosets, man, which is equal to the order of G divided by but H is the order of the stabilizer of epsilon 1 in G. Well, Right, the order. It's like all my favorite stuff is in this, right? Like you have it's the order of the group divided by the order of the stabilizer, which is the order of the orbit of epsilon1 under the action of G. But we already saw that G acts transitively under these conditions, and so this is equal to R. And so it must be, so if G is, if G injects into that group and it has the same order, G mod H is isomorphic to G of L over F. What? All my favorite stuff is in this, huh? Yeah. I need a suitably celebratory color here. I'll go with green. Yay. Very happy with that one. Okay. Whew. All right. That by God is a proof. And it's not my proof, so I can say that, but you know, that by God is proof. All right. So is everybody okay with our grand finale, or are there any questions? I guess we're not going to get to 17.8 today. That's okay. That's fine. Any questions about our grand finale here? Are we good? Should we move on? Do an example? Of course, the examples are the hard part. So everybody else, question or yes to move on? Right. Okay. So let's do. Yeah. Let's now, as you'll see in a minute, let's do an example where we actually get to put this normality business into action. Okay, which is the splitting field of x cubed minus 2. So here, the roots of this equation. Oops. The roots. Okay, let's see. So it's hard to keep writing that cube root. So let alpha be the cube root of 2, the positive cube root of 2, and let omega be the now I'll be more specific than that. Let omega be equal to e to the 2 pi I over 3. It's sort of one of the natural cube roots of unity. So that's our abbreviation. So I should blow this up so it's a little easier to write. Ooh, that's gnarly there. Okay, so the roots of x cubed minus 2. Oh yeah, so the splitting field of x cubed minus 2 over the rationals. This is an example we've actually seen before. Actually, as we brought up, it was actually an example we brought up as an example of a non-Galois extension, and we'll sort of see a different proof of that right now, I guess. So the roots of this equation are going to be alpha, omega alpha, and omega squared alpha. And remember, omega cubed is equal to 1. So this is, oh yeah, and it's also useful to note that omega bar is equal to omega squared. So let me renotate this. Instead of omega squared, I'll use my preferred notation for this, omega bar. Okay, so and we'll see that's sort of useful. Let's see. So one thing. So actually, let's just go ahead and compute the Galois group of this using the information we already know. So, so as we'll see, so G is the Galois group is a transitive, because x cubed minus 2 is irreducible. G is a transitive subgroup of S3. So it's G, either G is equal to S3, the full S3, or is equal to A3, the alternating, which is the same thing as cyclic on 3 elements, or G equals A3 equals C3. And so, however, here it's not too hard to see that here we have this one helpful explicit automorphism of G, which is that complex conjugation fixes alpha and swaps the other two roots. So G must be equal to S3 because A3 and the cyclic group of order 3 or the alternating group of order 3, same thing, do not have an element of order 2. So G equals S3. Let's see. So 2 elements of G must include the following permutations. So we know that well, actually we sort of knew that. So we kind of already knew just from the get-go that there has to be some sort of cyclic permutation. So there's one permutation which is alpha goes to omega alpha goes to omega bar alpha. So that's one permutation that we know has to exist. And we just said the complex conjugation. I mean, actually, I guess all the well, I'm not sure why I'm saying giving names to these specifically. Other than well, because all the permutations are in there because G is equal to S3, but still, it seems handy to sort of note them. Right. Oh, right. And what I really want to do here is I really want to draw the subgroup lattice. So this is going to be the trivial group. And remember, let's see. And so and then at the bottom we have S3, and then there's the cyclic subgroup generated by sigma, and there's always going to be and I guess the elements of order 2. Actually, so the elements of by 221A, or even by 128A, here are the elements. Those are the elements of those are the elements. Ooh, right. Those are the elements of the group G, and so all the subgroups are cyclic. Some of them have order 2, and some of them have order 3. So there's the subgroup lattice of. So there's the subgroup. There's the subgroups of G, and now when we draw the corresponding fields, we have our full splitting field K, and now and here's F, and so now what we want is some extension of degree 2 over here, and let's see. So right. So these are sort of a little easier to describe. So So if these are all going to be extensions of degree 3. So they have degree 3, and so their stabilizers have order 2, and so right, and so we so one of these is going to be omega alpha, and the other one is going to be omega. See, let me. Alpha goes to omega alpha. This is actually is. Oh, I'm confused. Okay, so I think next time. Well, no, I'm not going to chicken out of this. So one of these is going to be f of omega alpha, and the other one is going to be f adjoin omega bar alpha. And did I get that right, or did I get that wrong? Well, okay. So what is omega tau? So oh yeah. So sigma tau. What sigma tau? So sigma tau. I should just compute this, right? Sigma tau sends alpha to omega alpha, and it sends omega alpha to omega bar. Okay, yeah. So sigma tau, it corresponds to omega bar, and there, and then sigma squared tau corresponds to f of omega alpha. And let's see, can I figure this out? So what is it that is so that this is the real subfield, so we don't want that. Yes. So the thing we actually want here, it's a bit of a surprise, but this is f of omega, right? And so that's something, right? This is the one I can never, and so that's always the one that's a surprise here. I mean, so if you think about it, so omega, so note, omega is equal to omega alpha divided by omega. Remember, fields are closed under division. So omega is in fact in the field K. So one of the surprising things, there's all kinds of surprising things that you find out about field extensions. So it's sort of not obvious that when you're taking the splitting field of x cubed minus 2 over the rationals, that the cube root of unity is actually in that field. It has to be, but it's because it's the ratio of two things that we know are in that field. And so right, that's got to be it. And so and note that sigma of omega is equal to sigma of omega alpha over sigma of alpha. That's right, I did work this out. Is equal to omega squared alpha divided by omega alpha. Remember, because sigma sends alpha to omega alpha and sends omega alpha to omega squared alpha, and which is equal to omega. Right. So in fact, sigma does in fact fix f of omega. Wow. So that's as good a place to end as anything. We have this somewhat surprising result. And oh yeah, so this is let me just say one more thing about our normality result, because I have minus 1 minute left. It's fine. Minus 2 minutes left. So this over here is a Galois extension, and this over here is this extension is not. These extensions are not Galois because remember, this extension corresponds to a normal subgroup, and these extensions correspond to non-normal subgroups. Ta-da! All right. Sorry, ran 2 minutes over. It's just like old times, right? I went 2 minutes over. So anyway, thanks very much for your patience, and I'll stop recording and stop sharing, and see you later. Bye.